Welcome to the third and final part of the chapter, in which we will test the knowledge we have gained so far. For this, we now use the development board of the written curriculum. There's no need to worry for those who don't have one at home, as the steps shown in the video are generally applicable for sensors communicating with I2C. So this example may be helpful for other projects. Besides, we also walk you through the solution in the video, so that nobody will miss out on the fun. If at any time you get stuck or confused about what's happening, feel free to go back to the previous episode where we explain in detail how the light sensor works.
Before we delve into the ins and outs of coding, we need to prepare the scene. Our development environment is still STM32 IDE, so let's get started. Create a new project. File/new/STM32 project. Select the F405 VGTX microcontroller, as we have already done, and make the necessary settings. If everything has been done correctly, we should see the following pin and configuration window. Here you can configure and activate the peripherals of the microcontroller and set the operation of the legs that act as input and output. In our example, we will use the 4 LEDs of our board and the light sensor, so it is sufficient to configure only the corresponding legs. Let's start with the LEDs arranged in decreasing order from PD7 to PD4. These legs will be used as outputs. To do this, we need to find where they are in the program. Either we can run around all the legs by eye, or take the easy way out, we can use the leg search box. First, find the PD7 leg, then click on it and select as GPIO output. To make our code easier to understand, it is a good idea to name it. Right-click on the PD7 leg and select Enter User Label. Enter the name of the LED, which in the case of leg PD7 is LED1, since it controls this LED. Repeat these two steps for the PD6, PD5, and PD4 legs. While Donny is writing this, I will tell you how fast the I2C protocol can communicate. At the time of the video being shot, the I2C standard supports 5 speed classes. These are called the standard mode, with a speed of 100 kilobits per second, the fast mode with 400 kilobits per second, the fast mode plus, which can reach 1 megabit per second, the high speed, which can transfer data at 3.4 megabits per second, and the latest ultra fast mode, which can reach 5 megabits per second. The devices we use support only standard and full speed modes. For the sake of example, we'll use the basic standard mode and the associated 100 kilobits per second transfer rate. Let's set up our I2C peripheral, which will be used to communicate between the light sensor and the microcontroller. Microcontrollers often contain more than one of the same peripherals. For example, in this controller, there are 3 I2C peripherals, and we need the first one of them. On the left-hand side, select it in the connectivity group, and then look for I2C in the mode interface. CubeMX will then assign the required legs to the peripheral, which are PB6 and PB7. Often we have the option to port out the same functions to another leg. For example, PB6 is currently the SCL leg of I2C1, but we could also derive this to PB8. On our board, the I2C peripheral channel 1 is connected to the originally offered PB6 and PB7 legs, so we don't need to deal with that now. There are devices that use addresses longer than 7 bits, because over time, the 7-bit address range has proven to be scarce. The primary address length setting can be used to adjust its length. Our sensor has a 7-bit address, so we must not change the default setting. In the clock configuration tab, we can change the clock of the controller. Again, there's no need to change the default value of 16 MHz.
It's important to mention that for time-critical systems, clock speed can make a big difference. Therefore, it is worth keeping it in mind.
Yes, that's right. Next, on the Project Manager tab, under the Code Generator category, look for Generate Peripheral Initialization as a pair of C per H files per peripheral. This will write the functions that initialize the peripherals to separate files, which will make the code easier to read. When you're done, save and generate the code. The program that we will create in this chapter should be a simple progress bar that we can control depending on the illumination of the light sensor. You can download the completed project from the curriculum website. Let's not waste any more time, start working on the code. Let's start the interpretation at the stove, then move further and further away from it. The entry point for our program is the main function located in the main.c file. Let's see what happens here. Broadly speaking, the following things are happening. We start with initialization, which is done for us by the code generator, but it's useful to know the processes. The generator calls the functions of the units, which starts with the HAL library, and then prepares the clock signals. After that, the peripherals take their turn, and the GPIO and the I2C are put in a ready-to-run state. From now on, it's our job to code. Before anything else, we send the power on command to the light sensor. Then, at this point, we enter the main cycle, which starts with reading the value measured by the light sensor and then displaying it on the LED strip.
I like these talking names of functions and variables, because I can easily understand the steps of the cycle without knowing their internal content.
This is what sophisticated coding has to offer. You could have named everything here without meaning, and the program would run exactly as it does. The fundamental difference is that no one would understand it from the outside. If a few days or even an afternoon goes by, the person who wrote it won't necessarily understand it, so it's all useless. But now, it's not enough for us to have nice lines, we also need to explain how the light sensor works, so let's start with display first, and then we'll come back to the communication with the light sensor a little later. The value that we get from the light sensor is an unsigned 16-bit number. The reason it is unsigned is that there is no negative illumination, so we don't have to deal with handling values less than 0. The measured value will be compared to the constants at the beginning of the main.c file. Each constant represents the end of the range. For values below limit off, none of the LEDs will turn on. If the value falls within the range limit off and limit 1, the first LED will be lit. Beyond limit 1, 2 LEDs will be lit, and so on, until we reach a value greater than limit 3, where all LEDs will be lit. The constants are freely variable. For us, these values were the most demonstrative of the phenomenon. After the main function, you will see a function called error handler. This is used by the HAL library and our code when an error occurs. Our goal was to clearly see if an error occurred, so the LEDs are first turned off so that all LEDs are in the same state and then flashed at 200 millisecond intervals. Since there is a while one cycle in this error signal, the only way to exit is to restart the microcontroller. The light sensor read value and light sensor power on functions in main are not declared in main.c, but in the light sensor.h. This helps readability, as we don't have one long main.c file, but we break our code into several smaller and easy to understand modules. Extract the light sensor.h file. In it, we have created 3 enums. These are I2C light sensor registers, I2C light sensor address, and I2C usage mode. The enum I2C light sensor registers contains the address of the light sensor register. These registers were discussed in the previous episode.
If my memory serves me right, in the previous video, the control register was titled 0, and now I see hex 80. Would that be a typo? And if it is, why is it only noticed in the middle of the shoot?
This is a good point, but it's not a mistake. The explanation is that this IC has to be handled a bit differently than usual. For example, if you want to read the ID register, then you don't just tell it, well, let's go to your hex OA register. You have to say, in command mode, let's go to your hex OA register. This was interesting to me at first, so I'll explain it right now. The datasheet says that if you want to set a register, you can do it by adding hex 8 null to the address when writing the register. So, when addressing the register, we need to send the light sensor to the address hex 8A. Does that make the difference clear, Donny?
Well, that explains it all. We can go on learning about enums.
Okay. The second enum is the I2C light sensor address enum, which contains the possible I2C addresses of the light sensor. We've mentioned earlier that for addressing, the first 7 bits of the byte will be the slave address, and the last bit will be the direction of the data flow. The last bit is set by the HAL library itself according to the functions we are using. All we have to do is to add the start of the 7-bit address to the MSB. To do this, we need to shift the address to the left by 1, that is multiply it by 2. The I2C usage mode enum was created only because we wrote the power on and read value functions in 2 different ways. In the main.c file, when you call them, you can specify there how you want to use the function. In addition to the 3 enums, the prototypes for the light sensor power on and light sensor read value functions are also included in this file. We're making good progress. Only one more file to go. Let's find the light sensor C. In this file, we implement the 2 functions mentioned before. Both functions work in a similar way. You're given as a parameter the way you want to perform the operation, and then, in a switch case structure, the function corresponding to the way you want to perform the actual operation is called. The simple and memory-ended functions contain HAL functions and return their return values to the callers, who signal this to us if the operation fails by entering the error handler function we learned earlier. Continue the scan with the light sensor power on simple function. We now know that we need to specify the device address, the data direction, and the register to perform the operation on both read and write. That's what happens here. The HAL I2C master transmit function needs to be told which I2C peripheral to send to and what I2C address to use, from where, how many bytes to send, and how much timeout allowed it to perform the send. In the function, 2 bytes will be sent, since the slave device address is sent by the HAL function itself. One of our 2 bytes will be the register address, and the other will be the power on constant. We need to send this because we need to enable measurement on the light sensor. According to the datasheet, we can do this by writing the value stored as power on to the control register. With the light sensor power on memory function, we can manage our peripherals from a slightly higher level. Here again, we need to specify which I2C to use, which address to send to, which register to write to, and what to write. The main difference is that here we don't need to include the register in our data to send, as we specify it as another parameter of the sending HAL function. The light sensor has already started the measurement, we just need to read the result. This is done by the light sensor read value simple and light sensor read value memory functions.
I assume the difference here is that simple uses one HL function and memory uses the other. Am I right?
You're on the right track, but there are more differences than that. Let's look at the code in more detail to avoid any misunderstanding. First, look at the simple end. Here we need to implement the I2C write sequence we saw earlier. We first need to resolve the device register selection. To do this, we use a call to HAL I2C master transmit, where we specify the address of the register, but no data is sent into it. Then, we can start reading with HAL I2C master receive. This function has the same parameters, but now the pointer must be set to the location intended to store the received data, and the number of bytes received is specified. The received data, which is currently stored as two 8-bit numbers, must be converted to a 16-bit number. This number will be saved by the light sensor read value simple function to the memory space received as a parameter and return the success of the read as the return value. We've managed to write this in one line, which can be useful because it is much more transparent for the more experienced programmers, but beginners may have difficulty interpreting the many operators. The transformation to a 16-bit number is done on the right side of the equation. Take the top byte from the array and shift it 8 bits to the left so that it is in place, while 8 0 bits appear below it. Here, we insert the lower byte with the OR operator. And on the left side of the equal sign, we store the data in the pointer. When using our other reading function, we don't need to worry about sequence compliance, as this is handled by the HAL I2C memRead. We just need to provide the parameters mentioned earlier and sit back.
Finally, the long-awaited moment to test our light sensor has arrived. To do this, you must first upload the program to the microcontroller, which we have already done.
On the panel, I now find the part labeled light sensor and illuminate it with my phone. As I approach my phone, more and more LEDs light up, just as expected. When I remove it, there are fewer and fewer. If I cover it with my hand, a similar thing happens, although this obviously didn't surprise anyone.
Yes, it has worked there.
To provide flexibility for use in different projects, the example code is designed to make it easy to change the following parameters. The light sensor I2C address, the limits for turning off the LEDs, the turning on method for the light sensor, and how it is read. I encourage you to experiment with modifying these, or even read the other data register. After all, we grow by trying. The example has shown almost everything we've learned in this chapter, so it's time to summarize it quickly. In this chapter, we learned about I2C, one of the most commonly used synchronous communication interfaces in embedded systems. Another commonly used communication is SPI, which works differently but should be easy to understand. You can find more information about it in the written curriculum.
This chapter of the serial communication is at an end, but the topic is far from being fully covered. Therefore, we will continue exploring it in chapter 10 by covering UART, CAN, and USB in a broad outline. As usual, we'll include some other interesting things, so you should stay tuned there. Thank you very much for your attention, and we hope you have gained a lot of useful knowledge. The figures and source codes shown in the videos can all be found on the crystalclearelectronics2.eu site, under the 8th chapter of the curriculum. If you liked the video, give us a like, subscribe if you want to know when a new episode will be released, or follow our Facebook page for the latest information on the video series. I would like to express my special thanks to Szabolcs for his excellent performance. On behalf of all of my colleagues, have a great day. Bye.
Bye!